The kinetic-molecular theory, or the theory of moving particles, with regard to gases goes something like this. Gas particles are in constant random motion. Not all gas particles are moving at the same speed, but they're all moving constantly and in random directions. Secondly, the volume of the particles is negligible compared to the container volume. That is, the gas particles are spaced very far apart relative to their size and to the size of the volume of the container. Thirdly, the attractive repulsive forces between particles are negligible. And again, this goes back to the idea that the particles are spaced very far apart, so they don't really attract each other that much, and they're moving very, very fast. Fourth, collisions are elastic. What that means is there's no energy lost in a collision. This is not true in the macroscopic world. When two football players collide or somebody punches a wall because they're upset, that's not an elastic collision. Mechanical energy is not conserved in that case. There is a good deal of it that changes into heat. But with regard to gases, gas particles do collide with elastic collisions. Fifth, the average kinetic energy of particles is proportional to the absolute temperature. That is, the kinetic energy is proportional to the Kelvin temperature. Now, if you've taken physics, you might know that we calculate kinetic energy by taking 1/2 times the mass times the speed squared. If kinetic energy is proportional to temperature and kinetic energy is equal to 1/2 mv squared, then what that means is that temperature is proportional to 1/2 mv squared, and that means that the speed is proportional to the square root of the Kelvin temperature. At a given temperature, the gas particles of sample A have the same average kinetic energy as the gas particles of sample B. Because kinetic energy depends on mass and speed, if two samples of gas have the same kinetic energy at a given temperature, what that must mean is that the more massive gas particles must be moving on average slower than the less massive gas particles. So for example, neon, which has a molar mass of about 20, and argon, which has a molar mass of about 40, if samples of these gases are at the same temperature, the neon atoms must be moving and bouncing around faster than the argon atoms, because the neon atoms are not as massive, the argon atoms are more massive. Pressure is related to how forcibly and how often gas particles collide with the sides of the container. If I give you these two scenarios here and ask you in which container is there more pressure, you'll answer container B, because while there are the same number of particles, the particle in container B is moving faster, as indicated by the longer arrow. If instead I give you a case like this and say, in which container is there more pressure, here it's not quite as clear, because while each particle in container B is going to hit more forcibly, the more often component is going to go to the particles in container A. If I had to guess, I'd say container A, but here we can't really tell for sure. Let's do a couple other examples. If we have a mole of neon at 25 degrees in a 5-liter container, and another container, 5 liters, 1 mole of neon, but higher temperature, the particles on the right are going to be moving faster, so there's going to be a higher pressure on the right. If we repeat this, 1 mole of neon at 25 degrees in a 5-liter container, and on the right this time, same temperature, same volume, but now 5 moles of neon, clearly there's going to be more pressure on the right. Final thoughts on the kinetic-molecular theory. 1. The kinetic-molecular theory attempts to explain the observed properties of gases. For example, the filling of any container, compressibility, and the exerting of pressure. 2. The tenets of the kinetic-molecular theory are that gas particles are in constant random motion, have negligible volume, have negligible intermolecular forces, collide elastically, and have average kinetic energies proportional to Kelvin temperature. And 3, the kinetic molecular theory breaks down when confining pressures become very high and/or temperatures become very low. This is because, under such conditions, particle volume becomes a non-negligible fraction of the total volume, and because attractive forces also become non-negligible.